Okay, so yesterday no, it wasn't yesterday. 2 days ago, I guess. Um, I talked about Bachelor's law for passive scalar turbulence, and I related this law, at least heuristically, I related this law to the cat map on the torus. So you remember this toy model, that I had. Okay, I won't try to scroll all the way back to it. And I showed that this toy model using the cat map displayed Bachelor's law, which was a power spectrum on the passive scalar. And then I said, okay, then what we're going to try and do is we're going to try to prove that the Navier-Stokes evolution, stochastically forced Navier-Stokes, very important, kind of mimics or has some similar properties to this. Last time I proved that the Lagrangian flow map, so where particles go on the torus, as driven by the velocity field coming from stochastic Navier-Stokes, is chaotic in the sense of having a positive Lyapunov exponent. And this is similar to the cat map, which is very chaotic, but not nearly enough to prove what we want to prove. Because the property we needed for the cat map was that it mapped Fourier modes. So it took something at scale lambda and mapped it to lambda squared, where lambda is some power, some number bigger than 1. So it was a geometrically fast increase of frequency as a function of time. And that's what we need. That's actually what we're going to need. And so how we're going to quantify this is something known as mixing in fluid mechanics. And when someone in fluid mechanics says mixing, they mean literal, like mixing milk into coffee. It's not, so physically speaking, it's not any more mystical than that. So this is a picture, some beautiful pictures by Jacques Vanest, who's an applied mathematician. And that's really what we're interested in doing. We want to understand, how do we stir this red into this blue so that it's all uniformly white, either in a weak sense, or if you have some dissipation, then in a strong sense. And so this is a global thing. So just because the flow map might be sort of stretching exponentially, so having a positive Lyapunov exponent kind of means you locally look like a saddle everywhere. If you kind of ride the flow, everywhere looks like a saddle, essentially. That's what having a positive Lyapunov exponent means in a volume-preserving flow. But that's a very local property. So it says that you always have some direction which is expanding and some directions which are contracting. But here we need a global thing. We need to know that all of this blue gets interchanged with all of this red. And so mixing is actually a much, much stronger property. And as we'll see, like it's strictly stronger. So you cannot prove mixing if you don't, or you can't prove exponential mixing if you don't have a positive Lyapunov exponent. And so we need to improve our results. So how are we going to quantify this? So let's just think about the initial value problem of advecting a passive scalar. You want to understand, what does mixing quantify? There are many ways to quantify it. The most convenient way, I think, which is, it's pretty much always the most convenient way, is using negative regularity, like a negative Sobolev space is probably the most convenient way. And the reason why this is easy to think about is, imagine this term is not here for a second. So you just have this advection equation. Then the passive scalar is given by the composition with the inverse flow map. So remember, phi t is the Lagrangian flow map associated to, well, in this case, associated to Navier-Stokes, but whatever, just associated to some velocity field. And so the L2 norm is conserved quantity. And so if this negative regularity space decayed as a function of time, then the only way that could possibly happen is if all of the information, all of the sort of energy in G hat was shifting from low frequencies to high frequencies. Now, it's very important, so it's a small detail, but it's important to note that you will get always some kind of positive regularity on this side if you want to get a negative regularity on this side. This is because the problem is time reversible. And so if you want to know that you're shifting from low frequencies to high frequencies, you need to know that you're starting at low frequencies. Because if you start at high frequencies, you could actually shift from high frequencies back to low frequencies and then back to high frequencies again. So it's different. Right? And so this you should try to kind of think of is it's a little bit like the Fourier transform of dispersion. and dispersive decay is time reversible, but that doesn't mean you don't get decay, right? You just have to pay something. So in the Schrodinger equation, for example, you pay localization. So you get decay in L infinity if you start in L1. And here, you have to pay regularity. You get H-1 decay if you start in H1. Okay, so this is the kind of thing that we want to prove. We want to prove that exponentially fast, the H-1 norm decays, because that will tell us that the information is all shifting to high frequencies exponentially fast. Another thing to notice is this says all frequencies go to, all the information goes to high frequencies, or all the energy shifts to high frequencies. So this is much, much stronger than an H1 norm growth. So having a positive Lyapunov exponent you can use to prove that you have an H1 norm growth of the passive scalar, like exponential H1 norm growth. But this is much weaker, actually. This says that, okay, you can have like a tiny little bit of energy going to high frequencies exponentially fast. This H-1 decay says all of the energy has to go. So, in this picture, that's like pointing out that, we're not going to consider this picture mixed if there's some little red spot here. So if there's some red spot that kind of never gets broken up and never gets stirred into the blue, then it's not mixed. You missed some. So you can't miss anything. Okay. So there are two characterizations of this. So there's the Fourier transform version, which I definitely prefer because I like Fourier analysis. You can also get it by duality. And if you do it by duality, still thinking in the kappa equals 0 case, at least for a second, then you say, all right, I'm going to use this formula that GT is equal to G composed of phi t inverse. Plug that into this formula. If you look at integral of f against G, then by incompressibility, that's the same thing as f composed of phi t times G. And this is exactly, so if this decays exponentially, so we want to prove something like this, where we have H1 norms for both of these kind of test functions. This is exactly the notion of strong mixing or strong correlation decay in dynamical systems. And so actually that notion of mixing is actually the same as this notion of mixing. And this is actually, this duality characterization is going to be how we prove it. Well, sometimes we use both, but most of we use that. Okay, so now the main thing that we actually have to prove, which ends up being split into three papers, one of which I've already discussed, which is Lagrangian Chaos. We need two more, is this sort of capstone theorem about the mixing of the flow map. So there are lots of models which satisfy this property. You can see the papers for the big list. But in particular, stochastically forced Navier-Stokes and stochastically forced 3D hyperviscous Navier-Stokes. All right, so what it says is that for all new, so there's going to be this parameter p floating around. Let's forget about p for a second. Just think of p is equal to 2 for a second. Then there's a deterministic gamma, which does not depend on kappa. So this theorem is about this with the kappa. Well, we first had to prove it without the kappa, and then we had to prove it with the kappa. So there's a deterministic number independent of kappa, such that you get a random constant. So that this holds for all G in H1. Of course, everything is average 0. Everything I'm ever talking about is average 0. And so it's important to notice that gamma is deterministic, D is random, and it depends on the initial condition of the velocity field. But D, we have moment bounds. So we have estimates on how big D can be in terms of U, and this is independent of kappa. Okay, so this is what we mean by uniform mixing. So it's uniform in kappa exponential mixing, and it's almost sure exponential mixing. So it holds, so for almost every initial condition U, well, actually every initial condition U in our phase space, and almost every omega, D is finite. And you have this for all G. Okay, so if you fix U and omega, you have this thing. So it's important to see that this constant does not depend on G. That's really important. This D is only a property of the velocity field on the random noise path. And this D, of course, we don't know exactly what it is. It's really complicated, what determines D. But we do have moment bounds. So we know that it's unlikely to be super huge. This is actually getting, you can kind of think of this estimate as, well, you also have that the G in H minus 1 is just bounded by the initial L2 norm. So this is also just a true fact. And so this D is really a log mixing time. It's something to do with a log mixing time, because this estimate is useless until this coefficient is less than 1, right? And so this coefficient is less than 1 right about when 1 over gamma, right about when time is bigger than 1 over gamma log D. So polynomial moments on D give you exponential moment bounds on how long you have to wait in order to see the mixing. Okay, so actually, when I first looked at it, I was like, what, D should have exponential moments? Everything in the world should have exponential moments if you force with Gaussian noise. The physical thing, the mixing time, does indeed have exponential moments here. Okay, so this is a really hard theorem to prove. So the Lagrangian chaos is just the first step of proving this theorem. It required a lot more work on top of that, and that's what I'm going to sort of sketch today. Mostly I'm going to talk about this first paper. It's more than enough to fill the hour. That's where, yeah. But yeah, I'll talk a little bit about the second one at the end, and about the challenges for what happens when you add in kappa. Okay, so, sorry, one more important point that I want to make while I'm here is that this is optimal in the sense that you can prove, actually it's much easier to prove this, though not completely trivial. You can prove that there exists, again, a random constant D, sort of D prime, and a random constant gamma, a deterministic constant gamma prime, such that this holds. Well, I think the norm on G would be H minus 1 here. So you can prove that you can reverse this, and so this is always true, and this is actually much easier to prove. And D prime still satisfies this estimate, and gamma prime is still deterministic. At least for the kappa equals 0 case, this is how you would quantify that this is optimal. So this is qualitatively, so up to the exact values of gamma and D, this is qualitatively the fastest that the fluid could possibly mix anything. Okay, so it cannot mix faster than this. Basically, it mixes more or less as fast as it can. Okay, so how do we actually prove this? So what we want to prove is this, kind of almost surely. And we really want to know what, this random constant, we want to also get moment bounds. That's important. Without that, you can't prove Bachelor's law. You need at least two moments to prove Bachelor's law. Okay, so now there's a trick, which at least we learned from a paper by Dolgopiak, Korolov, and Koloshin, who also all happen to be at Maryland. Basically the idea is we want to prove this almost sure result. And one way to do it is you say, okay, well, we want to prove an almost sure result. So kind of course, naturally, you kind of want to use Borel-Cantelli. So you want to say the probability that this correlation thingy is bigger than some exponential is itself something like an exponential. This is what you kind of want to prove. Let's forget about trying to quantify these regularity classes. That takes a little bit of extra work. And then because this is now summable, then you would get, by Borel-Cantelli, an almost sure exponential decay. And in fact, by playing a bunch of more sophisticated games with exactly what appears here, you can start to get moment bounds on that random constant. So that's what we want to do. So we want to prove that this thing decays exponentially. Now, because we only know like 2 inequalities, one of those inequalities is Chebyshev. And so you use Chebyshev and expand the square, and you have that this probability is bounded by this sort of new expected value. And so now the point is that this allows us to switch from some kind of almost sure statement to, again, a statement in expectation, where it should be easier to use our probability tools. Well, in particular, what we want to do is we want to prove that this thing is decaying and exponentially fast. That's our goal, right? And so by choosing Q small enough, it suffices to just prove that this thing decays exponentially. And now you look at this and be like, okay, that's actually a Markov semigroup. This is a Markov semigroup applied to an observable, but the observable that it's applied to is actually what we call the two-point process, or the two-point motion, where I'm going to label two particles. So I have a torus, and I'm going to label two particles which are not initially equal, and I want to follow their trajectories as they evolve under the same evolution. Again, the motion of any particle or any collection of particles is not Markov, and we need a Markov process. So the Markov process is the velocity field and the two labeled particles. Okay, so it's still infinite dimensional. All the Markov processes that we have to deal with in this are all infinite dimensional. Okay, now this Markov process is a little bit problematic because it doesn't have a unique stationary measure. Okay, there is an almost surely invariant set, which is when the particles are glued together. So if x equals y initially, x equals y forever. So there's kind of two infinities. So there's an infinity when u goes to infinity. That makes sense. But we're going to have to treat x equals y, this diagonal, as part of infinity. Okay. Because what we want to prove is this. We want to prove that the stationary measure, so this is the stationary measure for Navier-Stokes. And this is going to be Lebesgue measure cross Lebesgue measure. We want to prove Navier-Stokes cross Lebesgue is the unique stationary measure for this process when x and y are initially separated. And we want to prove that this geometric ergodicity holds. So we want to prove that observables converge to their ensemble average with this stationary measure. So not only do we want to know that this is a unique stationary measure, we want to know that it's kind of exponentially attracting in this sense. So that's going to be the goal. So as it happens, it essentially suffices to prove this. And we're going to get a constant here, and you need a function of the initial condition here. Because if the particles start really close together, it's going to take a really long time to separate them. Because you need to separate them, and they basically need to become decorrelated and trace out the entire torus. Sorry, can you guys actually see me? I'm kind of doing like hand motions, okay? So that means you expect that this function v, or script v, goes to infinity when x is close to y, and or whatever, and not exclusive and u goes to infinity. So also if the velocity field is really, really big, so think of it this way. Suppose you start the velocity field to be a shear flow, like sine y comma 0. Except instead of sine y comma 0, you put 10 to the 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 10 times sine y comma 0. And you have a huge shear flow, and your noise is still order 1, right? And so for a really long time, the flow is going to stay kind of close to a shear flow, and then it's going to become unstable and break apart and do some stuff, and then the viscosity is going to bring it back and things like that. It's going to take a really long time. And so also when the velocity field is large, you have no idea what's going on. And so you won't be able to, this V needs to blow up also when the velocity field is large. Okay, so we expect that this V is singular. All we need is that this V is in L1 with respect to this measure. So it can't be too singular at the diagonal, and it can't blow up too fast at infinity. Okay, so we need V in L1. Okay, so this is our goal. So this is the goal of 95% of this exponential mixing paper is about proving this statement of the two-point motion. All right, how do we do that? So there's a number of classical frameworks for proving exponential ergodicity for Markov processes. We're going to follow a strong Harris framework because a lot of reasons, which I'm not going to get into all of them. But one of them is because we can, and there are some reasons why we sort of have to for now. Okay, so let me just state sort of completely abstract theorem which tells you how to get to exponential ergodicity for any Markov process on any Polish space. What you need, it's sufficient to get 4 conditions. So two conditions we've already seen before, which is strong Feller, which is this regularity property that it regularizes, the Markov semigroup regularizes observables. And the next one is irreducibility, which tells you that sort of everywhere in phase space is connected to everything else. Now, the next property is that I have some way of exponentially controlling deviations to infinity. The idea is that V, which is called a Lyapunov function, controls deviations at infinity. Which for us, remember, will mean when x is close to y or when velocity field is large. And so what it says is that you come back to sub-level sets of V exponentially fast. So of course you can always deviate. The solution will always be deviating arbitrarily large and then coming back, deviating arbitrarily large and then coming back. It's a stochastic system, of course. But you need to know that it doesn't somehow deviate too often or deviate too large too often. And you know that when it deviates, it has to come back. And that's what this controls, that the deviations come back exponentially fast. And then you have to have some condition that says the sub-level sets of V are important. And so what you want to know is that on sub-level sets of V, so sub-level sets of V, you know that there's a compact set where everything gets mapped into. And so this is essentially a property of parabolic regularization. So it says that, yeah, my phase space isn't compact, but as long as I stay controlled by V on sub-level sets of V, I'm going to kind of map into a compact set, with high probability somehow, with uniform probability, I think would be a better way of saying it. And this is actually not hard to prove. This is basically parabolic regularization if you have the right V. So as we'll see, for the two-point process, for the main thing that our goal is, the really hard thing is finding V and proving this. Everything else is kind of, well, maybe like 10 years ago would have been really hard, but kind of a solved problem, right? Modulo some difficulties, so it's not completely easy, but the hard part is actually this one. Okay, so now there's a theorem. So I'm particularly quoting a version due to Goldis and Maslowski, but the frameworks kind of have history that goes back much further. This particular version just happens to be stated in Goldis and Maslowski quite rather clearly. It says, if you have these conditions, then you're geometrically ergodic, and the space in which you're geometrically ergodic is actually an important detail, which I won't dwell on too much, but is actually very important for our work and for understanding infinite dimensional geometric ergodicity in general. So this theorem, the strong framework, so by strong framework, I really mean basically a framework that requires strong Feller, gives you geometric ergodicity in CV. So this is the same V that gives you the Lyapunov function. And so V grows at infinity. So this is actually not just bounded observables, but continuous bounded observables that could grow quite fast at infinity, as we'll see. And it says that in this class of continuous sort of controlled growth in observables, you get exponential convergence to the equilibrium, or sorry, to the ensemble average. So that's what this says. Okay. So the first thing that we have to do is control large deviations of the fluid. So never mind about the particles, we need to control large deviations of the fluid. Now, we have a difficulty which is not present in the previous works, which is we need to control large deviations of the fluid in a way, we need to control like fluctuations in the regularity of the fluid, not just in the sort of total energy of the fluid. And so proving that this is a Lyapunov function for Navier-Stokes is, well, here this is 2D. I have the H1 known there, is really classical. I think it's due to Flanderly and Maslowski, but maybe even earlier. I think they proved that this is a Lyapunov function in the sense that I just gave for Navier-Stokes, or for 2D Navier-Stokes. And it's not too difficult. So if you add this additional higher regularity, it's still not very difficult. But as far as we know, we didn't see it in the literature anywhere. It's not very difficult. But we need something much more than just proving this is a Lyapunov function. We need to control deviations in a much stronger sense. And what we have is this very complicated looking lemma, which basically is the optimal control on the large deviations that we could find thus far. So let's unpack what this complicated lemma says. Forget about all these conditions up top. Let's not worry too much about it. What it says is that I can put in the expectation. So notice I can put the supremum of time inside the expectation. So that's much more than what's actually required for this, because this is like expected value of V of UT. And so this version is already much stronger. Secondly, this grows, so I can increase the power as a function of time, at least for a little bit. So this you gain more. You gain more than just saying you go back to sublevel sets exponentially fast. You get the kind of extra contractivity. And on top of that, you can throw in this additional exponential time integral of some HS regularity for some HS regularity that's not too big. Okay, and that's going to be really important for controlling fluctuations of the particle motion. Because, you know, growths of gradients and stuff like that or like the control of two separate particles colliding or not colliding are all controlled by the exponential integral of the L infinity norm. So at some point, you really need to control this really, really well, very well. And so this lemma is going to allow us to control that very well. So this lemma, so this property of being able to choose a larger power here is very important. It's sometimes referred to as super Lyapunov. That's certainly a terminology we adopted because it's a good terminology, I think. But we need more than just the super Lyapunov. We really need this exponential time integral. So this you need basically the thing you need to control some of these higher regularity things. You need to really treat sort of high frequencies and low frequencies separately. So you need to treat sort of fluctuations in the low frequencies, are very different than fluctuations in the high frequencies. And so to wrap everything up together nice, you really need to sort of separate low frequencies and high frequencies when you do this estimate. And sort of, when you're at high frequencies, you have to use the fact that the viscosity becomes stronger and stronger the higher frequencies you are. And that's very important for controlling these large deviations in high frequencies. Okay. So with that, so I think maybe an easier to read variation of the lemma, which is actually suffices for many, many steps that we need, is this lemma, which is important to understand, which tells you that so for all k, so for any value k you put here, there exists deterministic C and k prime such that this holds. So what it tells you is that basically exponential time integrals with some regularity shown in are just controlled by a fixed deterministic exponential growth estimate. So this is actually one thing that tells you that even though our velocity fields are not bounded in time, so our velocity fields are, can become arbitrarily large. So they're not L infinity in time. Of course not. They're stochastic processes driven by Brownian motions. But it doesn't matter from a perspective of like, oh, maybe this can mix faster than deterministic fields that are bounded. Oh no, that's completely wrong. They cannot mix faster than bounded in time deterministic flows. Okay, and that's an important thing to understand. And that's just simply because the fluctuations at high frequencies are controlled, basically. Okay, so together with the strong Feller property and things like that, one can prove then that the UT process is geometrically ergodic. So at least the UT process is geometrically ergodic just using V. And geometrically ergodic in our phase space bold H, so in high regularity class in particular. Okay, so that is sort of a small piece of what we need. So the next thing that we need is we need to build a drift condition that controls the particles. So in particular, so we know when the velocity field becomes very large, it will come back exponentially fast and sort of faster than exponentially fast. It'll come back really fast. I should say this super Lyapunov property is not special at all to Navier-Stokes or anything. It's the Ornstein-Uhlenbeck process in 1D satisfies this property. It's really a process of, it's a property of kind of like having linear dissipation. Yeah. And in this case, you use subcritical, that your equation is either critical or subcritical. So the critical case is actually a little harder. So in 3D, we work with energy subcritical dissipation. And so at this step, actually, the 3D case is a little easier than the 2D case, because in 2D, it's going to be critical, energy critical. And you need to use the vorticity formulation and stuff like that. So you use like basically that at high frequency, the dissipation always wins. Right. It's an important fact. Okay. Right. So now what we need to do is we need to find some V, which is singular along the diagonal when x is close to y, and which you have exponential decay in this sense. Okay. So what does that mean? So actually, basically what we need to say is that when the two particles come together, we need to know that they separate again exponentially fast. That's actually what we're going to try to prove. And that is actually because of Lagrangian chaos. So let's think about that. So when x is close to y, you know the difference between x and y is controlled by the gradient of the Lagrangian flow map, and that thing's supposed to be blowing up exponentially. Well, we did prove that that's blowing up exponentially, right? And so, kind of heuristically, at least, forgetting about errors and fluctuation times and blah blah blah, that means the distance between x and y should grow exponentially fast when they're close together. So whenever they come close together, they should separate again as if they were being separated by an exponential. And so it would make sense to just do 1 over the distance of the two particles. So d here is distance of the two particles. We're on a torus, so technically, you have to be careful if you want to make sense of this x minus y, but who cares? So what I'm going to look for is, so what I really want is to do like 1 over distance to some power, and p is going to be some power which is close to 0, but positive. And then psi p is going to be where the hard stuff comes in. This is just a smooth cutoff to just say, this part of the Lyapunov function only turns on when the distance is less than 1 over 10 or something. So if the particles are separated by more than 1 over 10, it just is just this v, basically, which just controls the fluctuations of the velocity field. Now, psi p, so why do we even need psi p? What even is psi p? What is this for? So the reason it's going to be there is that, remember, the exponent, it's, gradient of phi is actually a matrix, right? So it isn't just about whether or not it grows. There's also like a growing direction and a contracting direction. And you need to kind of know how x and y will align. What's the, you want to know, for example, like, when they align on the stable manifold, they're going to come really close together or something, or when they align on the unstable manifold, they're going to have some kind of behavior. And so you need something that actually is going to keep track of the directions. And this psi p is the function that will do that in a sense. Okay, so now the idea is we need to find a psi p such that this thing holds. So now let's use this linear approximation. So if we take this linear approximation, so forget about this for a second. We take this linear approximation, put it here. What we want to do is study this semigroup, which is no longer a Markov semigroup. So what I want, it's called a twisted semigroup sometimes, or a Feynman-Katz semigroup. So it is a Feynman-Katz semigroup because you can write it as a kind of an expectation of an exponential time integral times this. So it's like a Markov semigroup with an additional exponential running time, running growth kind of. And so you have something like this. So this kind of is motivated by this. And what we want to do is, so what we actually do is we construct an exact eigenfunction to this semigroup. So we find a lambda of p, so that's some number, and we're going to prove that lambda of p is positive, and we find some psi p such that this holds. And psi p will actually be the dominant isolated eigenfunction. And psi p will also be strictly positive, which is important. So that's an important detail that I didn't quite mention. So that we need that so that we get some kind of coercivity. So this kind of property is going to be related to basically saying that it's coercivity. It's sub-level sets actually control things. So what you need to know is that if V is not too big, then the particles actually are separated, right? Otherwise, you're not doing anything. Everything breaks down when the particles get close together. All the strong Feller breaks down, all the irreducibility breaks down, everything breaks down. So you need to know that psi p is positive and, in some kind of quantitatively controlled way, so that if V is bounded, then the particles really are separated. So we have a sort of laundry list of things we know in psi p, and even more than that. You also need that psi p is regular, because at some point you're going to have to justify this linear approximation, which is actually in some sense the hard part. So let's first talk about how do you find a psi p and what capital lambda is, because actually capital lambda turns out to be a physically meaningful number. So it comes out from the derivation that lambda is actually this quantity, which is called the moment Lyapunov exponent. And it's related to fluctuations in how long if you're measuring the Lyapunov exponent, so if you're measuring the exponential growth of the flow map, it's going to fluctuate and do all these kinds of crazy things. It's not going to immediately equal the Lyapunov exponent. So what you get is you'll have fluctuations in that, and you want to know how quickly that converges. The finite time Lyapunov exponent sort of converges to the eventual Lyapunov exponent that we proved existed. So the first theorem we proved had no quantitative information at all. It said, okay, sure, you may have to wait 27 million years, but sure, technically, theoretically, eventually you'll see positive growth. Getting control in the moment Lyapunov exponent says that you sort of have exponential tails. You say, yeah, you're going to converge to the Lyapunov exponent like not too infrequently. It won't take you that long to converge. And that has to do with the fact that we've sort of put the expectation ends up inside there. So you need to control kind of the probability of the gradient of the flow map being really, really small in some sense. Okay. So the moment Lyapunov exponent it's a classical concept in random dynamical systems for this reason. So because it has to do with understanding these fluctuations of the sort of large deviations of the finite time Lyapunov exponents. And so there's sort of classical calculations from random dynamical systems which need to be carefully justified in the infinite dimensional case, but after some significant work can be done so. And so you can actually prove that this lambda p is actually differentiable at p equals 0. And you can actually prove an asymptotic expansion, and it's exactly equal to this. So it's p lambda 1 plus some smaller perturbation. And so here we use the Lagrangian chaos result as a black box lemma to basically say that Lagrangian chaos implies that lambda of p is positive. So that's where the Lagrangian chaos is used. Because the whole theorem of proving that there exists a lambda p and there exists a psi p and blah, 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 all of that works just fine, regardless of whether or not you have Lagrangian chaos. Here's where you actually use it. And even if you didn't have Lagrangian chaos, all of that would actually mean something in terms of these, how long it takes to see the Lyapunov exponent and stuff like that. But we don't directly care that much about that, except for this exponential mixing theorem right now, at least right now. And so this is where you need Lagrangian chaos. Okay, so how do you construct psi p? So it's hard, but it's not impossible, basically, because it's perturbative. Because we care about doing this for any p, which is, it could be super ridiculously small, and that's totally fine. And so what we're going to try to do is say, well, for p equals 0, this is the Markov semigroup for the projective process. So this ut, xt, vt process that we saw before. So this was you track one particle and a linear subspace, which is evolving according to, it's basically the normalized Jacobian. So it's, sorry, not Jacobian, normalized gradient of the flow map. And so it's kind of tilting in the directions where you see stretching and compression. So what we need to know is, so we're going to do a spectral perturbation argument. So we first need to prove that this p equals 0 guy has an actual spectral gap in some kind of function space of infinite dimensional observables. And you have a dominant isolated eigenvalue. And so the top eigenfunction is 1, and the dominant eigenvalue is 0 because it's a Markov semigroup. But you want to know that you have a spectral gap. Okay. So that everything else decays exponentially. And because you want to actually have you want to get a strongly continuous semigroup, and you want to get a real spectral gap and use spectral theory, you have to be a little bit more careful. And this was actually explained pretty well in a paper by Heyer and Mattingly on spectral gaps in infinite dimensions, which is, you know, in CV, the space of continuous and sort of controlled growth observables, it's not a strongly continuous semigroup because you're in infinite dimensions and everything is terrible. So what you have to do is actually you have to find this subspace called, well, we refer to as CV circ, this little ring on top, sort of math ring. And it's not quite the space of bounded observables. It's the space of sort of CV bounded observables, which are in the closure of spaces with which are in the closure of functions that are kind of finite dimensional. And you know, if you think about this for a little minute, you'll realize that V is not in this space. So V and V-like things is not in CV circ. Okay, so you need to but if you composed V with some kind of smoothing operation, so if you mollify the function and then put it into V, that would be in CV circ. So there's a little bit of problems here. So it has something to do with how much the observable sees the very high frequencies. But it's very dependent on what you call bold H and stuff like that. So if you look at our paper, there's all these regularity scales. We have a bunch of scales of Sobolev spaces and then scales of observables and then different V's and everything like that. I'm not talking about any of that. You'll just have to see when you read the paper. There's a lot of really annoying indices and you kind of run out of letters and things like that. Don't worry about it. It's not that important. The important is that you need this sort of reduced space CV circ in order to get good spectral theory. And so now we come across one of the big complexities one of the several complexities in the paper that we ran across is that the strong Harris framework that I just advertised gives you spectral gaps, for example, of this projective process in CV. Sorry, in CV circ. And so you can prove that there is a CP in CV circ, which is the dominant isolated eigenvalue. I mean, there's a bunch of work that needs to go into that, but it's work that we kind of already did. And so this is the Markov process we're talking about, and this is the semigroup for the projective process. But actually, because we need to justify a linear approximation, we need to justify this linear approximation. And that's going to turn out that we need to actually differentiate psi p. So that means we need psi p to be differentiable, and not just differentiable, it needs to be differentiable in the circ space. It needs to be C1V circ. And so now we need a spectral gap in a different space. So we need multiple spectral gaps in multiple different spaces. That we need to take, I'm not going to get into that because that's a whole nother thing, but basically Heyer and Mattingly have this really nice sequence of papers on how to do spectral gaps in C1V circ, or C1V, or geometric ergodicity in C1V, using their asymptotically strong Feller framework. And so everything that Heyer and Mattingly did, we also need to do for our process. So we need to use, so it's sort of a fun paper because we need to use both Strong-Feller and asymptotically Strong-Feller type estimates in the same paper to prove the same theorem. And I don't know how to do it with just one or the other. So you have to do all of that theory for our projective process in order to prove a spectral gap in the spaces that we want. Once all of that happens, then you can actually construct Psyche as a, you basically can, so you can construct Psyche as a perturbation, a spectral perturbation of the number 1. So the observable, which is just the number 1, that is the dominated isolated eigenvalue for p hat, because it's a Markov semigroup, and then we can transfer that kind of to p hat p. I'm skipping over some details because it's complicated and technical, and it's not, I mean, it's important, but you know what I mean. One thing I do want to point out before we even is that one of the technical details that you actually see, which we ran into very rapidly, is that it's not even obvious that in infinite dimensions this p hat p is defined. Or it's okay, it's clear it's defined, but it's not clear that it's actually a bounded semigroup in any space of observables, because you have this exponential integral here. So we need that super Lyapunov bound again, over and over and over again, to even prove that this thing is defines a semigroup on CV and C1V and stuff like that. Actually, doesn't define a semigroup on C1V. Okay, there are complexities on top of complexities that are technical, and I don't want to get into it. But essentially, long story short, we eventually, after a large number of pages and a lot of Molly-Van calculus, proved this. So the thing that we wanted to prove. And so we have a Psyche and we have a positive lambda. So that's cool. And Psyche is close to 1 in some sense and very regular for an infinite dimensional observable, at least. And so everything is good. But we're still not done, because in some sense, and I say it's actually the hard part because it's actually the part that took us sort of, in some sense, the longest to figure out how to do, which is how do you actually, once you have psi p, how do you actually prove that you have a drift condition? Because you need, well, psi p and stuff was designed to match this semigroup, not the actual semigroup of the 2-point motion. And this, we're actually going to use an infinitesimal generator argument, which is, so this is the Markov semigroup for the 2-point process. The 2-point process. So infinitesimal generators, they're defined in terms of the finite difference. And we have a nice strongly continuous semigroup on some Circ space for the 2-point process. But now it's an even more complicated Circ space that involves singularities at the diagonal and stuff like that. And so, okay, you can write this down formally and be like, yeah, for some domain this exists, but generally it's hard to know when this is, you know, if I give you a function, usually it's either definitely not in the domain of the generator or you just don't know. So it's hard to work with generators in infinite dimensions generally. But that isn't going to stop us here, actually. And in fact, you can actually prove that this part of the drift condition is actually in the domain of the generator, and satisfies this kind of differential version of the drift condition. And that is because this is kind of like time derivative of p, right? So this is why I say it's kind of like a differential version of the drift. This is a hard theorem to prove. You know, what you do know is that since psi p is an eigenfunction of p hat, so psi p is an eigenfunction of p hat, or p hat p, it's in the domain of that generator. And so you have some kind of generator leg to stand on, and then what you want to do is you want to justify the approximation of some version of p hat p, it's not quite p hat p, but almost, minus p2, and you want to control this as time goes to 0. You actually basically want to prove that goes to 0 in some space. And that's the second part. And oh yeah, and that's the second part. And that's like a problem. It takes some time. You need to use the entire full power of the super Lyapunov estimate that I gave. And I think this is the only part in the paper where you need to use the complete full power of that estimate. I'm not sure, I can't quite remember now. But remember, I gave this estimate that had, like, the supremum inside and the exponential time integral and the gain in the power. I think this is the only place in the paper where you need to use all of that at the same time. And so basically, because you need to really control kind of on infinitesimally short timescales very, very precisely the possible motions of all the particles and the velocities together. And it's hard to do that. Once you do that, everything else is kind of peachy and it works out. I think I'm starting to run out of time, so I don't want to get into it. But essentially, once you have this lemma, the other part is saying, well, V is a good, so things like you get this kind of decay plus an error, and this error is eaten by the V drift condition. So this is eaten by kind of parabolic regularity. It's like, it's somehow, like, even though you're in this infinite dimensional space and you're completely lost and confused, in the end, you're going to do the classic PDE thing where you're going to be like, oh, I'm going to negative term plus an error, and I'm going to take this error and eat it with the other guy's negative term. It's kind of like just doing an energy estimate all over again. Much more like just doing an energy estimate than it looks like. And so in the end, you're going to sort of, in the end, you're going to be able to prove a drift condition. And actually, you can show that lambda of p is the exponential decay rate of that drift condition for some suitably defined script v. And that's going to prove the geometric ergodicity finally. Assuming you also have to prove a strong Feller and things like that, but that's all easier. I haven't really even talked about that at all because I've been focusing on the random dynamical systems aspect. But you can never get away from hypoelliptic regularity in this life if you want to do stochastics. But I'm just not going to discuss it because it's only so many hours in the day. Okay, there's some last technicalities which I just want to alert you to, which is you have to somehow prove some control of the regularity. It's not enough to prove the geometric ergodicity technically. So you have to be a little more careful. You have to sort of apply geometric ergodicity Fourier mode by Fourier mode and keep track of frequencies and use the super Lyapunov estimate over and over again. You can get basically this, and then there's a nice little lemma that says that in the Sobolev scale, all exponential ergodicity is the same, essentially. And you can get to this. Okay. I think that's all I'm going to discuss on that because it's hard. The last thing, okay, I'm kind of out of time, but let me just say, including kappa is not straightforward. Okay, let me just put that forward because this is a singular perturbation. So just proving the theorem for this does not give you the theorem for this. And in fact, we have no idea how to say that if this mixes, then this mixes uniformly. I don't know how to say that theorem. I do know how to prove the theorem we want to prove, but it's, you have to go back, we use the stochastic Lagrangian flow representation, and then we have to do the entire theorem we just proved uniformly in kappa. And that's, well, it's an extra paper. So it's some serious work to do this. And it's not as hard as the original paper, but it's still some serious work. And requires, a number of new things, tricks. That's it. I don't have time to talk about bachelor's law. So let me just leave you with the end. As I talked a little bit about yesterday, what we're doing right now is kind of, as we saw, and I thought this was nice, is that like the sort of like the really like kind of subtle random dynamical, very random dynamical system Z argument, which I talked about yesterday, this a la Furstenberg theory, which when I first learned that, I thought it was just completely black magic. Now that I understand it, it's more intuitive. But at first I was just like, okay. The problem with that theory is that it's not quantitative. And we saw that all we needed was a little dose of black magic, and then we can just bring in all these super powerful stochastic PDE methods and just build and build and build and build on top of this little kernel of the positive Lyapunov exponent. But everything really depends on that. And so we really need better tools for estimating Lyapunov exponents and more general tools, more robust tools. And that's really what we're doing right now. For the goal of getting towards non-passive scalar turbulence problems. Anyway, so the moral of the story is we're still very far from proving, say, the Kolmogorov 4/5 law for Navier-Stokes or something like this. But I think that random dynamics is still the right way to go down in order to prove universality laws of turbulence, like power spectral laws and stuff like that. I'm not saying that every theorem that's interesting about turbulence has to be in a stochastic framework. I'm saying that if you want a theorem that very clearly is just like this experiment, if you want a theorem that can be matched very clearly to a specific experimental observation, I think that will have to be done in the random dynamics framework. And it might take years and decades, but not centuries, which separates it from the deterministic framework, in my opinion. And so I think this is the right proof. I think it's the right direction to go down. So that's why we're going down this direction. Okay, that's it.
Okay, great. Well, thank you very much for the highly impressive talks. And let's see, are there any questions?
Yeah, it was a little fast. But I want to give a flavor of the proof, not get bogged down in all these little technicalities, because there are a lot of technicalities, but you can sometimes lose the forest for the trees with all these technicalities.
Yeah.